So without further delay, I'll go ahead and introduce today's speaker. Today is Rob Van Kleeck. He's an MS student here at the University of Oklahoma. Originally from upstate New York, he received his bachelor's degree in atmospheric science from Lyndon State College in Vermont in May of 2018, where he researched winter weather impacts on electrical infrastructure, power lines, and wind turbines. He's also an alumnus of the 2017 National Weather Center REU program, and he now does research with Dr. Salesky exploring the impacts of urban boundary layer flow on point source pollutant dispersion using large-eddy simulation. Today, he'll be speaking to us about the effects of urban geography on point source scalar plume statistics through a large-eddy simulation study. So go ahead, Rob.
All right, thank you for that introduction. So I'm excited to share with you some of my preliminary research for my master's thesis. Some of this is preliminary, but some of the results that we have so far are very exciting nonetheless. And to get started, I'm just going to go through a bit of the background. Oh, what happened to my slides here? There it goes. So the largest motivation for this project is the fact that urban population is growing at a rate of about 2% of the total global population per year, and is slated to increase to about 66% of the total global population by 2050. That's 2/3 of everyone on Earth living in an urban environment. And tied to that, we have 33 megacities worldwide as of 2018, where a megacity is defined as a population over 10 million people. And with that, in cities especially, urban boundary layer and atmospheric dispersion are very pertinent to human health. Dangerous pollutants like particulate matter smaller than 2.5 microns are linked to lethal health conditions and have been estimated to lead to 4.2 million premature deaths in 2016, according to the World Health Organization. So we have more people moving to cities, more people in cities where risk of atmospheric dispersion of dangerous pollutants and chemicals and so forth are more of a problem. So we have an increasing risk, and we need a better understanding of how atmospheric dispersion plays into the dispersion of chemicals and pollutants in an urban environment. So we need to explore that a little more as the risk with more people moving to cities increases. And on that same subject, urban turbulence studies that focus on dispersion or just turbulence statistics itself typically focus on a small number of geometries available. For instance, the closest analog to this study, which was done by Phillips in 2012, only looked at 2 different geometries with a few different source locations for scalars. But the main thing is here that he only looked at 2 different geometries, and we really want to see what happens when we expand the geometry parameter space when it comes to how plumes are dispersed in an urban canopy. Similarly, Giametto et al. 2016, he looked at a domain that was based on LiDAR data centered on a Basel, Switzerland tower. And again, this is based on a real urban canopy, but it's only looking at 1 geometry. And in this case, they weren't looking at atmospheric dispersion, but nonetheless, varying how geometry changes in urban canopy is really important to see how the plumes and turbulence statistics vary with changing geometries. And similarly, Giametto et al. Also looked at a domain based on LiDAR data from Vancouver, British Columbia in the Sunset neighborhood of Vancouver. But again, the same story rings true here. He's only looking at 1 different geometry. Most of these studies, because they're computationally expensive, they focus on maintaining 1 LiDAR data set focused on 1 particular real urban canopy or idealized canopies of only a few or so. But we want to see what happens when you expand that parameter base and introduce more geometries to an urban canopy. Oh, that went too. And other studies in particular only look at street canyons, so they don't even look at the scope outside of a of the street. They only look at they don't look at the size of the urban canopy and things like that. But the key is here, there's little focus on a wide variety of geometries or exposure at a point. And we need to explore the relationship between if you change the geometry of an urban canopy, how will that affect dispersion and exposure statistics in that canopy. So that leads us to our 2 research questions as to what extent does the urban geometry, including alignment, packing density, planar and frontal area fractions affect the scalar plume moments, and how do the urban geometry and downstream location affect your exposure to the concentrations of these scalars exceeding some certain threshold. And we'll tackle both these questions subsequently. Now, just a little bit of background for people who aren't familiar with how large eddy simulations work. Large eddy simulations only resolve the large eddies in the flow. That's how they get their name. Subgrid scale models represent the effects of smaller eddies. Most modern large eddy simulations feature dynamic subgrid scale models. Typically, the filter length falls within the inertial scale. But the main thing to take away from this is that large eddy simulations are numerically cheaper than direct numerical simulations, where they resolve down to the Kolmogorov scales, and they're more detailed than the Reynolds average models that tend to stay toward the more integral and energy containing scales. So, and the result of that is that compromise between computational efficiency and what you're resolving leads to large domains where you can fit entire central business districts in the domain of the large eddy simulation. And this is really key in diagnosing scalar plume behavior in urban areas. If your domain was any smaller, you wouldn't have enough of a domain to see how the scalar plume evolves downstream. And if it was any larger, you wouldn't be able to resolve enough of the detail of the scalars to be able to diagnose the plume in the first place. So LES is really a very, very powerful tool when analyzing this. So now I'm going to talk about the large eddy simulation that I'm using in particular. It traces its origins back to a PhD dissertation by John Albertson in 1999. It's a filtered 3D momentum equation in rotational coordinates. It's pseudospectral in the horizontal, second order finite differencing in the vertical, and it features second order Adams-Bashforth time integration. This LES in particular is a dynamic subgrid scale model. In this case, it's Lagrangian scale dependent. And this model is neutrally stratified, which is one of the larger caveats to this study, but nonetheless, the results are very interesting henceforth. And the immersed boundary method and direct forcing approach are used in this case to allow for geometries to be immersed in the boundary. And essentially how that works is you have a wall that follows a coordinate system that follows the surface. So for instance, the slope surface in the figure on the right, the wall will be applied in a band above the surface using normal vectors at each grid point. In terms of scalars, the large eddy simulation uses an Eulerian finite volume solver for passive scalars. Cartesian cut cell method accounts for the geometry. There's a third order bounded upwind advection scheme, and conservative velocity interpolation of finite volume faces was added in 2008. Finite volume, face area, and volume fraction calculated from the level set function, and that enforces the scalar mass conservation that we need. And we're essentially solving the equation in the bottom there, but in our case, because we're looking at passive scalars, which are great analogs for small particulates smaller than 2.5 microns and noxious gases that are dangerous to human health in urban areas, we're not going to be considering settling in inertia in this case. The passive scalars are essentially just being evected in the domain. Now we're going to jump into a little bit of the parameter space. Now, for the moments that I'm going to be talking about, we're looking at idealized urban canopies where there are 10 meter cubes in each direction. It's a grid of them, and they all have a 1% slope to make sure that they correctly build a level set. Otherwise, you can get some weird numerical issues. There's some information about the domain size and the time step, but the main thing I want you to take away from this is that the periodic boundary conditions for momentum essentially emulate an infinite array of these cuboids in every direction, X and Y. There's inflow and outflow conditions for scalars at the boundary conditions, and the PGF is only imposed in X. That way, when you get any lateral spread in the plume, it's not due to a wind angle or something like that. It's due only to the momentum transfer from the buildings themselves. But how do we discretize the model? It's kind of always the tell with these things. So we ran some grid convergence tests to find the most optimally coarse resolution where we get enough detail, but it doesn't take too long, so that I never finish this. These are the results from that. We have the streamwise, spamwise, and vertical velocity variance on the top 3 panels respectively. We have the total stresses, including the resolve stress and the subgrid scale stress in the bottom left, and the turbulent kinetic energy in the bottom middle panel, all of which are normalized by the friction velocity squared. The line color denotes the resolution in question. The darker blue is the highest resolutions, and the lighter blues are the lower resolutions. And in our case, we found that the 192 cube resolution was the best candidate for momentum tests. It was a great compromise of seeming to follow some sort of convergence with a lot of these statistics, and also maintaining high quality and high resolution data while not taking quite as long as some of the 224 resolutions simulations were taking. So an overview of the idealized canopies that we're considering, there's a total of 12 of them. There's 3 different densities, and there's 2 different toggles for all those densities, where you have constant or random building heights and staggered and aligned rows. For now, I'm only going to focus on the medium density, constant height buildings. I've been testing the sparse and dense cases, but sometimes the LES is a little bit finicky with how it builds the level set function, and sometimes the MPI code crashes. So I've had some holdups with getting it started on the dense and sparse cases, but that'll be coming over the summer for sure. So the first idealized canopy we're looking at is the medium density staggered rows, constant building heights. You can see that each of the alternating rows down towards in the X direction alternate in terms of one full building height from one another. So leading to that staggered grid array type look. And then the other case is each a medium density aligned rows with a constant building height again. In this case, it leads to street canyons in both the X and Y direction. In these cases, all of them feature 96 cuboids with the same planar and frontal area fractions. For those who aren't familiar with planar area fractions, it's essentially the area of the buildings from the top-down perspective divided by the area of the domain from the top-down perspective. And the frontal area fraction is the area of the windward side of the buildings divided by the total area. Now, because of these buildings are the same dimensions in each direction, the planar and frontal area fraction is the same in this case. However, once we change some of those toggles that I talked about earlier, where you change the constant or random building heights, and where you change the density, then those values will change and will need to be accounted for. But now we need to figure out where we want to place our point source. So we're going to have a point source somewhere in the domain that is emitting passive scalars constantly throughout the simulation. And we want to develop Plume upstream or downstream of where the location is. So we want the location to be pretty close to the upstream boundary condition, but we don't want to get too close to that boundary condition. So we're going to place it equidistant from the second and third row in this case. However, when we're talking about a street, we really wanted to see if you place the source in the street, would it make a difference as to how the plume changes downstream? So we placed another source in the street and then one behind the building, of course, as you can see with denoted by the red circles. So that leaves us with three different cases of geometries where we have one where the source is in a staggered grid, and then two in this geometry where one is behind a building and one is in the street. But in addition to source location, we're interested in how source height affects these plume characteristics. So if we zoom in on where we placed one of the sources earlier, I created three more simulations from those based on the low source, a medium source, and a high source. Where our low source is typically around human height, about street level. Mid is about halfway up the building, and high is at the top of the building canopy. And altogether, if you combine all those parameter spaces, that's a total of 9 simulations where you have staggered, aligned, and street, and low, mid, and high for all of those. And then the last two, of course, have the same geometry as I just discussed. But if we have these simulations, how are we going to characterize the plumes from these? We need to make sure we're comparing them in a direct and meaningful way. So we can look at a Gaussian plume model where we compare the simulations of two orthogonal Gaussian plumes where there's a vertical and lateral spread downstream of dominant wind flow. This provides a basis to which to compare all the simulations to, as long as we can calculate both the vertical and lateral moments. And that will make non-Gaussian characteristics really obvious when we do that. And that'll be a really powerful tool to see how the plume is modifying downstream from the source. But how do we calculate these plume moments? Well, we can use this equation here where we calculate each of the moments where n refers to the nth moment. So for instance, n is 1 would give you the center line in whatever coordinate you're talking about. And if you look at the equation a little closer, a center line is essentially a center of mass for the plume itself. We also calculate the vertical moments because we need to compare to that Gaussian plume model. And for each of the moments, the second moment is spread, the third moment is skewness, and the fourth moment is kurtosis. And in a Gaussian plume model, the skewness is 0 and the kurtosis is 3. So we want to see how that compares to what we get from the results from the plume simulations. In addition to that, we want to make sure that we have fully developed plumes when we're talking about these simulations, because we don't want to just have part of a plume develop, sample that, and not get a correct idea of how many samples of a plume we're talking about. So thankfully, because they're integral statistics, they'll converge very fast, which is not the same as what we're going to talk about later, but we'll get to that. So we're going to run each case for a set number of time steps, which turns out to be about 18 large-eddy turnover times in our case. And in this case, the large eddy turnover time we're defining as the distance from the source location to the end of the domain divided by the average wind at building height. This is not the typical way of defining a large eddy turnover time. Usually you use friction velocity. But in our case, we want an effective time scale. In other words, how long will it take for the plume that's in the domain right now to advect out and for a new one to take its place. So we're getting independent samples of those plumes. Then we normalize each of the source locations in post so they're directly comparable. And each of them takes about a week. But what do they look like? So this is one of the simulations. We have a source that's aligned and behind a building and midway up the building. The contours denote the normalized and time average concentration on a logarithmic scale. And the lines on top of that denote the moments of the coordinate we're talking about. On the left-hand side, we have a XY slice with Z fixed at the source height. And we can see that the plume center line essentially follows the coordinate that we gave it. And then the spread around that is pretty obvious. And I've plotted the 1 and 2 sigma for reference. On the right-hand side, we have the same exact thing, but instead of looking at the horizontal moments, we're looking at the vertical moments in the vertical center line and the vertical spread around that 1 and 2 sigma. Now, one thing you'll note, the difference that's very obvious is with the vertical center line, it tends to oscillate around the buildings. And there's a very simple explanation for that. When you're over the street, your center of mass is going to be lower and closer to the ground because you have the scalars in the street. That's affecting your plume moment calculation. However, when you're above the building, there's no scalars in there. So your center of mass or the center line will go up, and that leads to that oscillatory nature you see there. You can also go across the plume with the figure on the left. We're cutting across the plume 12 building heights downstream from the edge of the domain, and it leads to this nice looking plume here. I've also plotted the center line and spread laterally at that exact Y coordinate just for reference. Nothing too surprising there. But we can also do is look at line concentrations. If we fix 2 of our spatial coordinates at different points downstream from the plume, we can analyze how the line concentration changes as the plume evolves. For instance, the left-hand figure crosses the plume at a given downstream location while holding Z fixed near the surface. And taking these slices at different downstream locations represented by the different line types there, we can see how the plume evolves downstream. And in fact, that the line concentrations that are farther downstream have higher tails on the left-hand figure, which means that it's spreading out laterally as we would expect. And further, the figure on the right shows a vertical profile of normalized concentration at those same downstream locations. And here the solid line hovers closer to the surface, meaning that the plume closer to the source is closer to the ground, which we would expect because downstream it's mixing up into the domain farther. And none of these plots are relatively surprising per se, but looking at the plumes this way could allow for an easy comparison to the Gaussian model that we just talked about if we normalize output from the LES and Gaussian model correctly. And this will be something to explore as I move forward with my master's research. But now that we're a little more familiar with how these moments work and what the actual moments relate to in terms of how the plume looks, let's look at the actual moments from all the simulations. Now, this is a lot all at once, so I'm going to walk you through this step by step. So as in each of the 4 panels, as you move to the right, your distance downstream increases from the source. The top left figure is the lateral center line, normalized by the building height, and the bottom left figure is the lateral spread. The top right figure is your lateral or your vertical center line, and the bottom right figure is your vertical spread. The line color denotes what of the 3 simulations we're talking about. In other words, the staggered, the aligned, or the street case that we just discussed earlier. The line type denotes the source height. So the solid line is the one closest to the ground, and the dotted line is the one farthest from the ground. One of the more obvious features that I see right away is the red or staggered spread laterally is larger in panel C than the other, the aligned or staggered spread. And this is because the staggered cuboids promote a lot of lateral transfer of the scalars outward. They're not getting advected down streets as much because there are no streets, so they keep getting advected outward from the where the source was. Another interesting note, in panel B, the vertical center line is quite a bit lower in the street case than the other, or the green lines, than the blue or red lines, or the staggered and aligned case. And we would suspect that the street would have a lower center line because of channeling in the street. So if your source is in the street, then a lot of the scalars that are constantly being emitted by that source are going to keep getting advected downstream and not get it lofted above by any buildings or obstructions. So your center of mass tends to be a little lower. Now we're moving into the third and fourth moments. We have the same orientation here, where the left-hand panels are your lateral moments and your right-hand side is your vertical moments. The top panels are skewness and the bottom panels are kurtosis. So in panel F, one of the more obvious features is a non-Gaussian convergence in the vertical, typically around 8 to 10 building heights downstream. Another feature that of note is the kurtosis in lateral and vertical is quite a bit larger for the street cases than the staggered or aligned cases. The green lines are higher in the kurtosis plots. And again, this is probably attributed to channeling in the streets, because kurtosis, if the values are higher, it means your tails are lower and your scalars are much more focused around your mean. So if that's what would exactly happen if you're in a street and the scalars are just constantly getting advected down that street canyon rather than getting wafted around buildings and henceforth. We can also look at maximum concentration downwind from each of the simulations. What do I mean by that? Well, we take the normalized concentration, that's time averaged, and then look at where the grid that has the maximum value of Cmax, and just plot the difference between each of those as a function of downstream location. And again, we see that the street case has a higher maximum concentration downwind, which would probably be attributed to channeling once again, especially because the dashed and solid line green lines are higher than the dotted equivalent, which means that the low and medium sources have the most channeling, which we would expect as well. So interesting results there. So some conclusions quickly from that. We have staggered buildings that allow for greater lateral spread in the plume. There's non-Gaussian convergence in the vertical, especially with that kurtosis plot, or excuse me, skewness plot. And the street sources have smaller plume tails, higher kurtosis, especially near the source, which is again attributed to the channeling that we talked about. In other words, the source height has minimal impact compared to the location and geometry. The line type didn't really denote too much of a difference between a lot of the plume moments. Location and geometry are much more important, which is exciting news for us, because that's what the whole point of the study was, to see how plume moments change as a function of location and geometry. So source height is not as important as we might have originally thought. So maybe from henceforth, we might consider that as less of a parameter space to test compared to location and geometry for the other cases I still need to finish. So we're going to switch gears a little bit now. When you're talking about dangerous chemicals and pollutants, plume moments really only paint part of that image. You don't really get the full scope of what's happening. And as John C. Wingert, author of Turbulence in the Atmosphere, once said, when he was referring to an incident in chemical incident in 1960s that killed a lot of sheep, he said, it's not the mean quantity that kills a sheep, it's the fluctuations. So with that being said, how do we quantify those fluctuations? How do we quantify instantaneous exposure to scalars and pollutants? So thankfully, the large-eddy simulation we're using can give filtered instantaneous values of momentum and scalar concentration at virtual towers in the domain. So what I mean by that is you choose a fixed spatial coordinate in X and Y, and the code will give you each of the filtered values at each time step for every vertical grid point in that domain. So 192 vertical grid points. And that's a lot of data. Each tower is tens of gigabytes. But how do we know where to place the towers? We could just say, put them in some respective location, fix the domain dimensions, and change the level set or change the geometry, and that would be fine. But if we want to really get objective with this and make sure that we're looking at this from the least subjective way possible, then we want to use a more data-driven approach. So what we can do is use the data from the plume moments to determine the location of the towers. So again, here's the slice that we looked at earlier of the plume looking downwind of the source. Now, if we go along the lateral center line, the white line you noted there, we can place 3 towers along that when the vertical center line following that reaches certain heights as a factor of the building height we're talking about. And then we can place 2 more towers at plus or minus 2 lateral spread from those towers. And that leads to a grid of the 9 towers that we see there. Now, the problem is they're not in the best location all the time, so we have to move them into the street, the nearest street canyon we can, so we can get the really interesting statistics that we see in the street level or where the human height would be. So that's the element of subjectivity into this, but we figured it was relative, and it suggests a region where we should place the towers, which we thought was good enough for the comparison between geometry and scalar statistics in terms of instantaneous exposure. So what does the data look like? Well, this is just an example to show you how chaotic the data looks. On the x-axis is time, and on the y-axis is your normalized concentration. But how do we know what these data, if it's any good, if it's supported by literature? We're not really kind of shooting in the dark so far. Well, what we can do is we can look at joint probability distribution functions for some of our variables at a certain height. So here we're choosing a height at the top of the building height. And we're looking at 3 different JPDFs. One features the streamwise wind and the scalar concentration. The other features vertical velocity and the scalar concentration. And then the third is purely your momentum statistics from U and W. And the scalar concentrations with U and W JPDFs, 1 and 2, I should say, are pretty homogeneous at this level. There's not much of a correlation. However, the third one features quadrant 2 and 4 domination when it comes to the momentum JPDF. So that's ejections and sweeps, which is supported in a lot of literature, including from Shemecki's 2013 paper, where at the same height that I'm talking about, he actually got a strikingly similar 2 and 4 quadrant domination like that. And I've also put the correlations here just for reference. But the point is that the literature supports how the data works so far, so we can move forward with how we're going to quantify exposure statistics with the towers. So we want a probability density function of exposure times for a set threshold, similar to what Shemecki did in his 2013 paper. And if we can relate that to geometry and placement in the domain, then that really hasn't been done to our knowledge. But what do I mean by exposure time PDF? Well, if we bring up another example of tower data where we have the mean as the 0 line and the 1 and 2, plus or minus 1 sigma spread around that as the dotted red lines, we can set an arbitrary threshold denoted by the dotted black line, where we're 0.25 sigma above the mean. And we can say anything above that is exposure time cumulatively. But what we can also do is separate them out into each individual event. So we can say count how long it takes, it takes for it to go above that threshold to go back below. And that would be one event, one exposure time. And what we can do is we can count those and get a PDF of them. Or in this case, we have a histogram of exposure times for that threshold featuring one specific tower. Now, the problem with this is if you really want a clean PDF with exponential decay and exposure times, you need a lot of data. And just from preliminary tower mitigation or tower studies here, we're only looking at the center line in this case for a particular simulation. So we have the 3 towers that are along the center line, west being the most upstream and east being the most downstream. And there's not really a discernible difference between the exposure times here. We need a lot more data. And because this is in one simulation, but 3 different towers, this is an intra-simulation comparison. However, if we move to an inter-simulation comparison, there's still no discernible difference between how exposure times are a function of some set threshold. But the idea is there to compare these exposure times as a function of both placement in the domain for an intra-simulation comparison and as a function of simulation itself for an inter-simulation comparison. So, but the takeaway from this is we need more data. We need longer simulations. I can't get the amount of quantified threshold events that we need with just the same amount of data that we got from the Plume Moments. Those converge a lot quicker. We need tons of data for these exposure PDFs, and I'll have to end up running these for probably about a month each, just to make sure that we get enough data for each of those. So just to wrap things up with future work, I need to expand the scalar Plume Moments to the other available geometries. I've already been going at this, but it's been a bit of a holdup with all the chaos that's been happening the past month. But the end result is hopefully going to be a full suite of sparse, medium, and dense geometries and moments related to those geometries in a great relationship that builds on the results from the medium densities that we've already looked at. And perhaps I could explore variable building height cuboids if I have time, but we'll have to see. And then I want to investigate other ways of comparing plumes. Scott and I have talked about this recently, where if we compare those line concentrations to that Gaussian framework, that would be a really easy way to spot non-Gaussian features in the plumes. And as I just mentioned, we need to characterize exposure for much more significant events. The 0.25 sigma threshold is not a very large, that's not a very stringent threshold. We need larger events and more of them. So we need to run tower simulations for at least 100 large-eddy turnover times. And if we do that and we get very clean looking histograms, then we can develop an objective comparison between the exposure PDFs. So now I'd like to make some acknowledgements here. I'd really like to thank Scott for all his help with this. He's been unwaveringly helpful when it comes to troubleshooting the model itself, or keeping my head up when the model tends to not work for no apparent reason. But he's been very clear about explaining things that I would otherwise have no idea how the model works, but he's very good at explaining that sort of thing. So I'm eternally grateful for that. Also, I'd like to thank Dr. Brad Alston and Dr. Petra Klein, my committee members. They're very helpful in kind of broadening the scope of this project and honing it down into a more applicable sense. And their insight is very valuable. And then, of course, I'd like to thank faculty and staff within the School of Meteorology, family and friends near or far. Most of them are far right about now just because of the circumstances. And then, of course, I'd like to thank my partner, Alexandra Barunda. She's been very, very helpful for me to get through this research so far. So with that, I will leave up my references and take any questions.
Great, thanks. So if anybody has any questions, they should be able to unmute themselves now and go for it.
I'll ask a question. I forget if you mentioned it, but how long, in terms of like your turnover time frame, does it take for your plumes to reach like a steady state where you're getting your statistics from?
I did a lot of testing with that last year. I ran them for a fixed number of time steps. There's 300,000 time steps with a time step of 5 times 10 to the negative 3, because we have very small grid spacing, so we need a very small time step. But they seem to converge very quickly, at least after 10 large eddy turnover times, I would say, by how I define them. They converge pretty well, but I wanted to make sure I was doing more than what was needed to converge, just to make sure that we have a really essential suite of the moments.
Rob, this is Petra. You mentioned that you see the non-Gaussian behavior when you look at the vertical concentration distribution. To what extent is that just because of the surface, because your plume basically cannot penetrate into the ground?
Yeah. So that's pretty much that's the largest explanation for that there. That's why I didn't focus on that too much. It's similar to how the center of mass oscillates around the buildings as well, and how they depend on where you are in the domain. That's why that wasn't the most interesting result for me. A lot of that is due just because the surface is right below you, but that's why I like the fourth and second order, or the fourth moments in terms of the street canyons, because I think that's a very telling signature of channeling in the streets. Does that answer your question?
Yes.
Hi Rob, this is Qingmiu. I'm curious how many kinds of input data have been used here for the simulation?
Input data? Oh, I see what you mean. Oh, I probably should have mentioned this. So for all of these moments, I ran momentum tests for just about as long as the scalars ran for themselves to get well-mixed, or mixed is maybe the wrong, well-developed flows off of just momentum. And then I started these simulations off of those restart files. So it was well-established momentum flow. And then we just had to establish the scalar flow to get the plumes that we needed. So I'm inputting a restart file with a well-established momentum for all of these simulations. And all the restarts are based on the geometry that we're considering. So,
do you have any observation data as input?
No, that's one of the caveats to this. This is a purely modeling approach. That's the idealized sort of aspect of it.
Right. Makes sense for me. Thank you.
Yeah, of course.
I have one more question. Can you go back and show how you normalize the concentrations?
You mean on the contours?
Yes. So,
so the right-hand side there.
Yeah, and the velocity, so you have the mean the concentration times, what are you using as velocity scale?
That's the friction velocity, and I define the friction velocity as the maximum in the covariance between momentum in the domain, averaged in the XY. So usually you use U star as like if you're talking about just a pure channel flow, you would define U star based on the covariance averaged right near the ground. But here I defined it as the maximum value in the covariance between U and W averaged over that. So that's how we're defining the friction velocity. And then we're normalizing by the building height and the strength of the source.
So does your friction velocity, do you have different, I'm guessing you get a different value for the staggered and aligned array?
For the friction velocity?
Yes. Or is
slightly.
it the same value?
They're pretty similar. They're very slightly different because I think that's largely attributed to how the planar and frontal area fractions are pretty similar. U star was typically around, I would say 7 or 8 for all the simulations, but I did keep the U star for each simulation by itself and normalized by that. So I didn't use a fixed U star, if that's what you mean.
Mm-hmm.
I calculated U star for each of the simulations and normalized it based off of that. So they're directly comparable.
And why did you decide to use a friction velocity and not a mean velocity?
Well, in this case, we were defining the friction velocity based on that covariance, like I said, but we decided to use that here just because it was convenient from how I calculated when I was using them, when I was doing the momentum or the grid convergence tests. U star was really important in that. So I just ended up reusing that code and normalizing by U star and then the building height and the Q source. It's a little different than how we defined the large eddy turnover time, which is often usually defined in terms of U star. But there we wanted an effective time scale. And here it was for the sake of convenience and the fact that U star helps to really get everything in terms of non-dimensional values.
Yeah, I don't know if you ever will attempt to possibly compare your results with other results in the literature, then it might be you might want to check in terms of what they use as velocity scales, because often the mean velocity is used there as well, because the idea behind it is coming from the advection, and that you are advecting if you go back to how the Gaussian plume model is even derived, then you basically assume that your plume gets advected, because then you run into the question of what velocity would be describing how your plume gets advected. So
that's a very good point. Yeah, sorry.
The reason why I even asked this, because had you used, I found it curious to see that the maximum concentrations, if I remember it right, your maximum concentrations were the highest in the case of where you have channeling flow, correct?
Yes.
That's the green.
Yeah.
Where you're, and you know, if you just think about the advection, you would expect there to have the highest velocities kind of in that channeling flow. But your plume, probably the spread of the plume, it remains very narrow.
Yeah.
But I was curious to see to what extent this result might be due to, is this a normalized concentration here?
Yeah.
Or is this, okay.
So I need to look into how I'm normalizing this a little closer. That's something I actually realized after I made this, is that, you know, as you just said, some of the velocity statistics might impact this in a way that I can't see yet. So the normalization on this is one of the more challenging things to keep track of. So I agree that I need to look at the normalizations for this plot, and that's actually a large factor in this as well, because I almost was able to get a Gaussian model equivalent on top of these concentration plots, but normalizing those in a certain way was a bit challenging. So I'll have to look more into how I'm normalizing to make sure that I'm making objective comparisons between. That's an excellent point.
Any other questions for Rob before we wrap up? Okay, well, then I think we can go ahead and wrap up this session. Thanks everybody for tuning in, and the recording will be uploaded later this afternoon. So thanks everybody.